In this video, we're going to talk about integrating a function over a curve. And so this is coming off of our last class on vector fields. So we're not going to talk about vector fields exactly in this video, but we will see them later on again. And so when we talk about a path, we're going to denote it as x of t. We're going to say it's c1, just generally to make things nice. And also we want to make sure that the derivative of our path is not the zero vector. And then just a couple quick reminders here. When we're talking about a path, we have two tools that we've studied before. We've studied the arc length function, and we've also talked about the speed. Okay, the arc length function, if you remember that we wrote as s of t, and that was equal to some lower boundary to a variable upper boundary, and then that was inside, it was the derivative of our path, and then we used this dummy variable tau, d tau, and that whole thing represents the arc length. And so that'll give us from, again, the length of the path from a point to a variable boundary. And then the speed, we talked about that as ds dt formally, and so if s is our position function, but we also said that here in this context it's also the derivative of our path. The length of the derivative of our path. Okay, so just a couple of quick reminders. Now, kind of the central question that we want to talk about in this video is, how do we integrate a function? And here I'm assuming it's a scalar function, so we have n inputs and we have a one-dimensional output. So we want to talk about integrating that function along a certain path. And so my first follow-up question is, what does this even mean? Well, we might need to go back to Calc 1 and do a little bit of thinking here. And just as a FYI, I do have the next image here, also in GeoGebra, that you can look at. Okay, and I'm just going to get rid of this screen shade. So, let's say we have a function given as shown to the right in blue, light blue that is, and then the path x of t is shown in black. Okay, and then so if we wanted to think about this, you could explore this with the GeoGebra file that I have included, but it would be this idea that, well, oh, no. We want to look at the path as it would be projected onto this surface, or onto this function, if you will. Okay, and so the integral, well, if we think about integrals from Calc 1, an integral is just the area between, the area between the function and the x-axis, right? So really, what the integral should give is the area between the function and the path. Okay, so if we think about kind of connecting lines here, it would give that would actually go up there. It would give the area between the path and the function. Okay, so if you want to write that down, we'll capture that here quickly. Between path, which is x of t, and function, and this, I'm going to say this is f of x of t. So I guess it would be the function when restricted to the path. Okay, and so to do this, we're going to go back and remember our old friend Riemann sums, the building blocks of an integral. Okay, and if you remember that, what we ended up doing is taking our interval, or our interval for, or our domain of our function, and making a partition of it. So what I did here was I took that A and B and split it into n pieces, and so it's x. I ended at n minus 1 because I began at 0. Okay, and so with this, I'm going to say, well, okay, well, we need to come up with this idea, and we remember that Riemann sums, there was something about rectangles going on, so let's try and mimic that same process here. Okay, I'm going to try and leave that on the screen, and here we go. All right, so we're going to pick some interval k, and so maybe let's just for our purposes here, let's say I'm going to pick this blue interval. Okay, and so I'm going to pick that interval and focus on that one. I'm going to call that the kth interval, and I'm going to look at the making a rectangular area. Okay, well, I need length and width, and then that's the area, and then I just have to add up all the areas. Simple enough. Okay, well, here's a question. Okay, so I need the length, and I need the width. Oops. Okay, and here length, I'm actually going to use the term height instead, because that might make a little bit more sense here. So I'm going to use, instead of length, I'm going to call that height. Okay, so the height might actually be the easier thing to find right off the bat. So according to my drawing, and again, this is just the drawing, kind of the height of this rectangle, that's given by, and if we can think of that path just as being in the z equals 0 domain, that's just going to be f, oops, and I need to stay consistent with my notation, that's going to be little f of x of t. And the primary reason for that is when we look at x, x was just a path and it was meant to be kind of one dimension lower. But so that's going to be the height, and I should actually clarify that it's not just t, it's t k, and then I'm going to use the symbol tk star to represent some value, and I'll write this down, tk star is in that kth interval. So then that kth interval is going to be represented as tk minus 1, comma, t of k. So it's just some point in there. And historically, you might remember we use left endpoints or right endpoints or midpoints, so it could be one of those. Okay, so that's just the height. And now for the width. Okay, well, the width, if we look here, that's actually going to be kind of the distance. I'm just going to write this. Well, I might use a different word. I'm going to call it, the width is actually, follow me here, trust me, I'm going to say the length of the kth segment of our path. Okay, and so yes, I could follow the path, I could also follow the function. I'm gonna go along the path, and you'll see why in a moment. Well, wait, the length of a segment along a path, isn't that just arc length? And I'm gonna denote this as change in s, so the change in the arc, change in the length, and I'm going to include a subscript for the particular interval I'm looking at. And so this is going to equal our arc length formula, tk minus 1 to tk, and then magnitude of x prime of tau. Oh, well, yeah, it doesn't much matter. D tau. Okay, so just to recap, the area, so to find the area of this little rectangular region, I just kind of did the same thing that we knew from Calc 1 with Riemann sums. I found the length and width of it, or the length, which I also called the height of it, and that's just going to be given by the difference in the function, so the difference from the function to the path, and at some representative point in that interval, and then I needed to find the width, which was just, if we were careful, it's just the distance along the path that we travel, which I called length, and that's just arc length. So then the area is just going to be the length, or the height, so f of x of tk star times delta s of k, and just keeping in mind that this is actually an integral. Okay, so now again, that was just for the first, or not for the first, but it's for the kth interval. So guess what we have to do? Well, we have to find all of them. Okay, so total area, which is our integral, this should be the sum, the sum from k is equal to 1 to n of f of x of t k star times delta s of k. Alright, and keeping in mind that delta s of k is an interval, and then if we want a better approximation, we remember we have to take the limit as n goes to infinity. Great! Go do it on all the problems. Okay, so in practice, this is the theory behind it, but in practice we're going to see we have something else that we can do in the next video.